Hello, good morning all. Um, so in today's class, in fact, the previous lectures which I had posted online, pre-recorded lectures, we discussed about the PMMC instrument, that is permanent magnet moving coil instrument, and then electrodynamic instrument. So in this class, we'll discuss about moving iron type of instruments, and I hope that uh, you could go through, you had the time to go through those lectures. Fine. So, in fact, you must have seen already that PMMC and moving electronic instrument are deflection type of instrument, wherein the quantity of interest develops a particular type of movement in the pointer, and that pointer movement is calibrated in terms of the quantity under measurement, whether it is voltage, current, or something like that, right? So both PMMC and electrodynamic instrument can be used for as ammeter or voltmeter. However, electrodynamic instrument is mainly suited for power measurement, that we'll see later on when we'll discuss about power measurement techniques. Okay. Uh, in the case of PMMC, we have seen how magnets are utilized, how magnet is utilized to create a magnetic field within which a coil rotates depending on the amount of magnetic field which is generated once the current passes through the coil, right? So a similar type of arrangement is there in the case of moving iron instrument. The schematic of that is shown here in this figure. As you can see, uh, it it is of two types. One is attraction type moving iron instrument, other is repulsion type moving iron instrument. So in the case of attraction type, you can see that an oval shaped lightweight iron disc, which is shown here, as you can see, a moving iron piece which is shown here, and it has an oval shape, and it is pivoted along the axis of the coil. As you can see, this is the coil. If it is shown, yes, coil cross sectional view shown here. So the coil carries the current, and which develops a magnetic field inside this, and depending on the magnetic field, the moving iron piece which is pivoted here, you see, it is pivoted. So these are counterweights to balance the weight of the pointer and the moving iron piece, and you can see that along this axis you have a pointer which is attached to it, right? Now, depending on the magnetic field, we know that the movement of the moving iron piece will occur. Now, how do we quantify that? In fact, the moving iron piece will get magnetized depending on the magnetic field generated by the current flowing through the coil. So let's say H represents the magnetic field which is generated by the coil, then the disk magnetization M is proportional to the magnetic field into sine of the deflection angle theta and the angle which it makes this iron piece which makes when there is no movement. So when theta is 0, whatever is this angle the major axis of the oval shaped iron disc makes with the vertical line here, vertical axis here, so that is this phi. So theta plus phi is the total angle once some amount of current flows through that and the pointer is getting reflected by an angle of theta, right? So that both the angle together decide the uh, amount of magnetization which is present, and the force with which the rotation occurs, this as you can see here, which is shown in this direction F. It is slightly dark but it is visible, I hope. That force is also proportional to the amount of magnetization, the product of amount of magnetization and the magnetic field. And since the magnetization itself is function of the magnetic field, then force becomes proportional to the h square component into sine theta plus phi. Now, who is generating this magnetic field? this magnetic field is generated by the current flowing through this coil, isn't it? So you see nice view of this cross-sectional view of the coil, current carrying conductor is shown here. You see, so the amount of current is going to decide the amount of magnetic field, and since they are proportional directly, one can see that the force of rotation required for rotation is developed in proportional to I square, that is current square. So this is simply a scaling factor sine theta plus phi. So you can see that the how much torque is there, which is acting as a deflection torque, is similar to the deflection torque which we discussed in PMMC instrument, that is given by F into L cos theta plus phi. Now this is the force component in this direction, which is used for rotation, F into cos theta plus phi. L is the you can say the point of application of force, the distance between point of application of force and the axis of rotation, right? This is the distance L. Now, since force is proportional to I square, torque is clearly proportional to I square, isn't it? So this torque is deflection torque. Now you can see that this portion, you see, this portion is the air friction which is created for damping the system, and if you remember our discussion in the case of the, let me just write it down. So the deflection torque is in this case is proportional to I square, right? In this case, so these are simply constants, and the angle of rotation is theta, right? Now if you remember our discussion on PMMC, that in the steady state deflection torque is equal to the controlling torque, right? And the controlling torque itself is proportional to theta, isn't it? If you remember, so this indicates that our angle of rotation theta is proportional to I square, right? Now where was theta proportional to I square? If you remember, it was in electrodynamic instrument, isn't it? Theta is proportional to I square there, and that is why it is categorized as non-polarized instrument. That means it doesn't matter in which direction current flows, since it is proportional to I square, it is able to measure AC quantities. The same is applicable in the case of moving iron instrument. In this case, however, if you remember previous discussion, the current carrying coil was rotating, right? But here what is rotating? An iron piece instead of the coil. So the outer coil is the one which is generating the magnetic field. That's all, right? So this is the basic difference between our electrodynamic instrument and the moving iron instrument. But the underlying principle is the same, and the relation between theta and I square is also same. And since it is non-linear, the scale, as you can see, it is cramped on the lower side. It is more cramped, and it is spaced on the higher side of deflection, right? So this is non-linear. This is non-linear scale, right? Okay. Now, depending on the apart from the we can say moving iron attraction type, here the iron piece is getting attracted, okay, towards the direction in which the magnetic field is generated. So this is categorized as attraction type moving iron instrument. As I mentioned, there are other type of moving iron instrument which can also be considered as repulsion type moving iron instrument. So in this case, you can see that there are iron bars or rods which are attached to the moving system placed along the axis of coil. As you can see, these are the iron bars. Now, uh, so this is fixed to inner coil of the body. So you see there is one here which is fixed, and this is one which is moving along with the pointer, okay, which is attached to this axis of the coil. Now here what happens is that the force of repulsion generates due to the current generated magnetic field. Now here you see this brown color region. These, if you look closely, these are wires. Okay, these are coil. This is a coil with through which the current flows and then generates the magnetic field uh, within this region. Now, due to this magnetic field, the same uh, magnetization occurs in the two pieces of this iron, and since it is the same, there is a force of repulsion among them. But one is fixed. You see, one is fixed to this coil. This one is free to move. Right? This one is free to move, and due to the force of repulsion, this moves and it moves the pointer along with that. Okay, and this is known as force of repulsion. Now, apart from the iron bar or rods, you have tongue shaped iron strips. You see here, the construction is almost similar, just that instead of the bar or instead of iron bar of this shape, rectangular shape, you have this tongue shaped iron strips. You see, so the larger one, if you are able to see clearly, if my pointer is visible, larger one is fixed to the coil in the inside part of the coil, but this one, smaller one, uh, smaller tongue shaped strip is attached to the axis on which the pointer is mounted. Right now, since both are going to get magnetized by the same magnetic field, there will be a force of repulsion among between these two strips, which will cause the rotation of the pointer. Okay, now again, similar to the previous one, these two these two are nothing but the counterweights. Okay. So this one can also consider that it is like a concentric vein moving iron instrument. Okay. Now there is a nice video with, which indicates this the practical moving iron instrument. So you see here, uh, you see this is a pointer which is moving. See, this is a pointer. It's a quite old instrument. It seems like that. Now, uh, then the so you see the coil. You see, this is the coil through which the current flows, which we are trying to measure, and then there is a, you see, within this is a fixed vein. Huh? This is a fixed part of the moving iron type, and it is tapered. As you can see, this is tapered to generate a linear motion, the linear variation in the repulsion plate. And now you see that inside this is a tongue shaped. Is it? It is clearly visible. The tongue shaped iron strip. You see, which will cause the rotation. And you see, this is a spring. This will impose the controlling torque. You see this brown color coil. Yeah, this is the spring. Okay, and these are the counterweights. You see, this is the shiny one is a counterweight. I hope it is clear with this video. So this is how moving iron type instrument work. Basically, principle is almost similar to your moving any moving type instrument. However, the moving component is different. Previously, it was coil. In this case, it is iron strip. Now, what are the advantages? The advantages, as I mentioned, since it is proportional to I square, not I, uh, it is a non-polarized instrument, uh, whereas uh, the it can be used for as an ammeter or voltmeter. We'll discuss that how one can use this type of instrument as an ammeter or voltmeter. And then because of the construction, it is inexpensive to manufacture, it is cost effective, and it is robust to the external environment because there is no permanent magnet which is used into this device. What are the disadvantages? Similar to electrodynamic instrument, the scale is not linear, so it is not easy to calibrate the instrument. And the operating current, that means the current which is required to generate the deflection of the pointer, is significantly higher. So in milliamperes or so, whereas in the case of PMMC, even microampere is sufficient to develop the required amount of deflection. And um, it has limited AC frequency operation, that at high frequencies it will not able to respond to the rapid variations in the current or voltage. And there will be some errors associated with hysteresis, because as we know, wherever magnetic field comes into picture, hysteresis is a part of that. And let's say if you bring external magnetic field in in the vicinity of the instrument, that may also disturb the system, because we know that the working principle is function of magnetic field H, right? So we assume that H is developed by the current carrying coil. However, if you bring external magnetic field, that will completely change the relationship between amount of deflection and the current flowing through the coil. Okay, so these are few disadvantages, or probably you can say limitations, associated with moving iron instrument. Okay, uh, moving ahead, we'll discuss about electrostatic instrument. And in this we have again two types. One is based on, let's say, uh, force of attraction, similar to moving iron instruments, and force of repulsion. So in the case of attraction, we utilize the electrically charged plates. uh, Now since it is electrostatic instrument, what we are going to do is the electrostatic principle, where the two plates which are having opposite charges or similar charges will exert some force. Now depending on the charge, there will be a force of attraction or force of repulsion. Now when the electric charged plates with opposite polarities are there, then there will be force of attraction. And when they are having the same polarity, they exert force of repulsion. Now as you can see in this diagram, the rotary motion of electrostatic instruments, where we again use the spring as a device which exerts the controlling force. And you have this you can say triangular shaped plates. Okay, imagine this as triangular shaped plates. The green color plate is fixed plate, and the blue color plate is a movable plate. Okay, now when the movable plate moves over the fixed plate, there is a variable uh, uh, variable area of overlap between the two plates, isn't it? Right. Now can someone tell that on what quantities the capacitance between the two plates depends upon? What is the formulation of capacitance? Capacitance is between two plates.
Distance between the plates.
Distance. Okay, distance
Area
between
of
the
the
plates.
plate.
Area of overlap.
Area of overlap and sorry,
Permittivity.
permittivity. Right now, when the distance between the plate is fixed, uh, how does the capacitance vary with the area? Is it will increase with the increasing area, or it will decrease with increasing area?
Proportionally.
Directly proportional.
Directly proportional, right? So in this case, as you can see that um, the due to the movable plate, the area of the or area of overlap will change, isn't it? So that depends on the angle theta, that is with the amount of with which the movable plate is moving over the fixed plate. Now fixed plate is fixed, as the name suggests. It is not moving, only the movable plate is moving. So one plate is moving with respect to the fixed one, and that is going to decide, you see, area A, area of overlap, which is shown here with uh, darker gray color here. And once you remove the amount of voltage supplied to these plates, the spring will bring back it to the original position. Okay, so one can treat this type of instrument as a variable air dielectric capacitor, right? Variable air dielectric. Why? Because the area, the region within the overlapping region consists of air as a dielectric medium, and it is a variable air dielectric medium because the area of overlap is changing depending on the angle of rotation. Right? Now, in this case, we have different types. So let me first discuss about a simple example. Uh, then we can move ahead to the quadrant electrometer part. Okay. Uh, okay, fine. Then I think we'll discuss quadrant electrometer part and then the two parts and the analysis of that. Okay. So this is for understanding the principle of electrostatic instrument. But in general, to increase the sensitivity of these type of devices, which are mainly used for voltage measurement, because this device, since it is working in the principle of capacitance, uh, is not going to consume any current apart from the initial charging of the plates. There is no current which flows. Okay, so basically it is highly suitable for voltage measurement because it is not consuming any current. The energy consumption will also be quite small. Now, the construction of quadrant type electrostatic voltmeter is made such that you can consider that you have a circular box. Uh, you can imagine metal box, some bigger box you can say, and similar to your pizza, if you, let's say, cut it into 4 parts, which is shown here. That's why it is quadrant type electrostatic voltmeter. It is cut into 4 parts. Okay, so these are 4 discs. Now this is a top view of the instrument. If you look from the side view, okay, it looks like this. Okay, this is the disc. The internal portion is hollow. It consists of air. Okay, so I hope it is easier to imagine from these two perspectives. One, this is a top view, this is a side view, and these discs are basically fixed plates of the capacitances, and there are 4 separate sectors of thin circular shaped metal boxes which act like fixed plates, and there is a movable plate which is inserted such that it rotates along the axis centered on the center of the circular shaped metal box, you see here. But its shape is like a butterfly shape. You can see this is shown in a dotted line. You see, this is like this. Now this is inside. It is shown in dotted because it is inside the box. So when you look from top, you will not be able to see that. Just that this region is still it is visible. Okay, this region, right? Now doubles sector shaped pivoted vein. So this is a pivoted vein, or it is also called as needle, rotates within the fixed frame. So you see it rotates in this region. So this is the, this is nothing but this. Hmm? Fine. It will rotate. Now in some cases, instead of one pivoted disc, to increase the capacity of the quadrant voltmeter, quadrant type electrostatic voltmeter for voltage measurement, there are multiple discs. You see, multi electrode quadrant electrometer consists of multiple such arrangements. So this is one pair, right? So you can attach multiple one, but remember the rotating axis is the same for all, so they are attached together. So they will move together within this metal box. I hope it is visible clearly, or uh, for the understanding purpose. And there are two ways one can connect these voltmeter for voltage measurement. One is known as idiostatic connection. Other is known as heterostatic connection. Now, in this, as you can see, in the idiostatic connection, um, basically, since we are trying to measure the voltage, we want to supply the unknown voltage in such a manner that it develops a field between these two plates, which will generate a force of attraction and repulsion. And then, depending on the amount of voltage I'm applying, the polarity, that will rotate the pivoted vein within the metal box to a certain angle that will indicate the amount of voltage that is being applied. Okay, so as you can see, there are four sectors, right? 1, 2, 3, and 4. So the diagonally opposite, sorry, diagonally opposite fixed plates, sectors. Which sectors? Fixed plate sectors, the fixed one, are connected together. As you can see, this is termed as positive. This is positive. This is negative. This is negative. So these two are connected to terminal EA, positive, and then negative. These two diagonally opposite sectors are connected. Okay. So what does it mean? That once I apply voltage here, such that the polarity is positive here, negative here, the charge developed in these plates are positive in this case and negative in this case. Okay, right? And then the voltage that is to be measured is applied here as EA minus EB, potential difference. So let's say V is the one I'm trying to measure, which is EA minus EB. And you can see that this pivoted plate which is moving is connected to one of the plate, one of the terminal. So in this case, it is connected to EB. Right now, we'll see the derivation that how it is proportional, the amount of deflection, and how one can utilize this instrument for voltage measurement. The other connection is known as heterostatic connection, in which the other arrangement remain the same. So this positive and positive diagonally opposite are connected to EA. These diagonally opposites are connected to EB. Fine. However, the moving plate, the moving vein, one can say, is not connected directly to EB, but there is an external supply voltage, power supply E1, which is attached, and it is this plate is now at much higher potential in comparison to negative plate as well as positive. That's why it is shown with three positives here. As you can see, it is at much higher. So E1 is much higher than the voltage we are trying to measure. Okay, is much higher than voltage we are trying to measure, and it is an external power supply which is required. You see, in this arrangement, you don't need external power supply. Here, you need an external power supply, and we will see the advantage associated with of using heterostatic connection. We'll see that. So in this case, one can express. So let me draw the diagram and then probably explain the energy, the derivation associated with the voltage measurement using electrostatic voltmeter. So since, as you can see here, these connections. So if I look at this portion and this portion, they are symmetric, isn't it? They are symmetric. So if we can analyze only one portion of that, so let's say this is one sector, this is the other sector, right? And the movable vein is, let's say, when there is no current or no voltage applied, it is symmetric. Now there is, similar to this, there is another sector here and another sector here, and there is another vein here, but because of symmetry we are not analyzing that. Now initially, let's say this vein is such that this angle is alpha. Okay, and once you apply the voltage, depending on the amount of voltage, there will be a deflection and it will move to, let's say, this position. Okay, so it has rotated in this direction, and this angle of rotation is, let's say, theta. Okay, now if I look at this from side view, now this is a top view, right? If I look at it from side view, it was like this. Isn't it? So one of the terminal was connected to A, other was connected to B. Now this is the movable plate, and these are fixed plates. Now if you look at this arrangement, this is like two plates at different potentials, isn't it? Two plates at different potentials. So you can see that this is one capacitance, this is another capacitance, right? And this is one capacitance, this is other capacitance. Now due to the symmetry in these two cases, because this distance and this distance is same, okay, these two are like C1 and C2, sorry, C1, C1, C1 dash, C1 dash, and this is C2 dash, C2 dash. Okay, two capacitances. Right? Now we know that C1 dash, let's say, it is epsilon A by D. A is area of overlap, and D is the distance between these two. Let's say distance between these two is D. This is also D, and this is also D. This is also D. Now, in this case, C1 dash is epsilon A by D, where A is area of overlap, which in this case can be obtained as 1 by 2 R square. That is, R is this R. Okay, this R, this R. 1 of R square alpha plus theta. So when theta is 0, then the area of overlap is 1/2 R square alpha for both C1 and C2, because it is symmetric, right? When theta is 0, it is symmetric. However, the moment it moves in this direction, the area of overlap with this sector is more in comparison to the area uh, uh, of overlap with respect to this. So that is where this difference between C1 dash and C2 dash comes into picture. Otherwise, when theta is 0, C1 dash and C2 dash are same because A is same, D is same, epsilon is the permittivity associated with the air medium. Now, this is A for C1. So C1 dash is epsilon r square alpha plus theta by 2D, and C2 dash is epsilon r square alpha minus theta by 2D. Okay. Now you see the C1 dash is area of overlap between these two and these two is same. That is this, and these two and these two is same. That's why C1 dash and C1 dash both are. Now can someone tell these capacitances, are they connected in series or parallel? So this is, let's say this is at some potential V. Are these two capacitances are connected in parallel or series?
Parallel.
Parallel, right? So when two capacitances are in parallel, what is the effective capacitance?
Add them and you will get them.
Right. So C1 dash plus C1 dash. So the C1 total capacitance comes in becomes epsilon r square alpha plus theta by d. Fine. Similarly, C2 is epsilon r square alpha minus theta by d. Okay. Fine. Now we need to look into the energy stored in the capacitance. This is the energy stored in the capacitance. Now, so this is V. Now energy stored. Hello. Yeah. So it is 1/2 in the first case. C1. What is E? Potential difference between the two capacitance. So now this is at EA, right? And this is V. So I will write V. Let me write it as V moving. No, so let's say VM. VM minus VA. Or let me use E only for this. EM. So this is EM. Right, energy stored in that capacitor, whereas energy stored in other capacitor is 1/2 C2 EM minus EB square, isn't it? Fine. Now in the torque which is required to produce the coil moment is given by this expression, where we need to basically, this is derived where the theta is derived from here. Okay, so this is the energy stored in C1, energy stored in C2, and we simply add them together and compute its derivative with respect to theta. That change in energy with theta will give me torque, right? So if you calculate the torque, it will come like come as this, where the basic torque equation. So in this I have used E1. E1. Okay, it is EM. Okay, EM. So if you evaluate this, then one can easily obtain the expression for torque, which is used to produce the coil movement, or not coil movement, other disk movement by an angle of theta. Now here, if you simplify this one, you will get this expression. So let me again replace this em. Okay, if you simplify this expression further, em square minus em square will get cancelled and you will get this expression. Now if you focus into this part, now one more thing I must mention here, that once you analyze this, the torque which comes out is epsilon r square by 2d into this expression. And since along with these two there are other two sectors which are also there, and due to symmetry the total torque will be double than this. So this 2 in the denominator and numerator will get cancelled and you get this expression. So the point of understanding you need to have is only this part, that torque is now function of the potential of the moving plane and the potential difference, the potential of the supplied voltage terminals, these two. Now if you focus on one of the connection type, means either idiostatic or heterostatic. As I mentioned, in idiostatic connection you maintain the potential of the moving plane at one of the terminals. So in this case, since it is connected to EB, what is EM in that case? EM is equal to EB, right? So in this case, so here EM is E1, it is equal to EB. And let's say if I apply the voltage which I want to measure across this and consider this as my ground terminal, then EM becomes 0 and the developed torque is now proportional. Now apart from the constant K, it is EA minus EB square. EB is 0 basically. So it is EA square, the voltage difference between these two into square. Whereas in the case of heterostatic connection, your EM M is again 0, where I have connected the voltage. And let's say this is, I've connected like this. This is also grounded. This is V. So I'm measuring the voltage V using this instrument. So EM minus EB is nothing but V. So if I consider EM as 0, which is there is some mistake here. This is not true for idiostatic connection. Right? So in that case, if you look at this expression, if you remember, I told this EM is much larger than the voltage difference we are measuring. Let's say we are measuring voltage from 0 to 5 volts. Then this will be
Sir, you've been muted.
So you're not audible.
Sir, you are muted. Hello, sir. You are muted, sir.
hello. Hello.
Yes, sir. Now you are
How
audible.
long I have been muted?
While you are talking about heterostatic, you are muted, sir.
Okay, fine. Thank you. So in the case of heterostatic connection, I was mentioning that due to the utilization of this EM, that is this connection, I'm utilizing EM as E1 in this case, okay, which is at much higher potential in comparison to the potential of these four disks. We can replace this term with simply 2m, okay, practically, and because of that, the deflecting torque is not now proportional to voltage square, but only voltage difference. You see, voltage difference square, but not voltage difference square, but voltage difference. What is the advantage with this? Since torque is directly proportional to voltage, my scale becomes linear. See, this is non-linear scale. Okay, so the limitations associated with heterostatic is that you need to use external power supply, but the advantage is you get linear scale, and the limitation associated with idiostatic is that the scale is non-linear, because similar to, if you remember, our electrodynamic instrument, moving iron instrument, the torque is proportional to I square. Here it is proportional to V square, that is voltage square. So it is still non-linear. But in the case of heterostatic, due to use of external power supply, we analyze, and based on the analysis, we come to know that the scale is linear in this case. Okay, fine. Now, we talked that the PMMC instrument is capable of measuring current as well as voltage. So can we use electrostatic voltmeter for current measurement? Can we use it for current measurement? It is not possible, because the torque is not proportional to current, but it is proportional to voltage. Okay, so this is basically designed for voltage measurement purpose only. So the advantage is that the current consumption by the voltmeter is almost zero, apart from the direct voltage which we get initial current for charging the plates. Apart from that, and it will occur in very like fraction of time. So apart from that, there is no current the meter consumes. Why this is an advantage? Can someone tell? It doesn't consume any current means what?
Power consumption.
Yeah, it can be more specific. It will not have loading effect, isn't it? Right? It will not have loading effect. It is not going to load the voltage we are trying to measure. So this is an important advantage. It is, and it has non-polarized terminals because of this arrangement. In the case of idiostatic connection, it has non-polarized terminal because it is proportional to V square, and it measures the RMS voltage regardless of the waveform. So many cases we assume that the AC supply is like this, but it may not be the case. Sometimes the AC might be like this also. When there are harmonics present in the voltage we are trying to measure, then one cannot consider it to be pure sinusoid. It consists of multiples of sinusoid consisting of harmonics, right? So even in that case, this type of voltmeter is going to give us the RMS voltage. So RMS, what is RMS? I have already discussed in the previous lecture, root mean square voltage, which is equivalent to your DC voltage, right? And since it works on the principle of electrostatic property, the magnetic field is not going to affect the performance, external magnetic field, and it is basically suited for high voltage measurement. Now the disadvantage is that, again, is that it is not capable of measuring current, so it is only used for voltage measurement, and especially in the case of idiostatic connection, the scale is nonlinear. And again, due to, we know that the capacitance has a filtering effect at high frequencies. We have limited frequency operation. We cannot go beyond a certain frequency range for which one can utilize this for, as a voltage measurement. Okay, fine. So apart from this, I wanted to discuss one more point. Let me include that part which we skipped during the discussion of PMNC instrument. Okay, so let me quickly go through that in next 5-7 minutes. That is about galvanometer. So basically, galvanometer is also a PMMC instrument only. And we have already discussed the working principle of PMMC instrument. Okay. However, it is designed for, it is highly sensitive, you can say. And it is used for extremely low current measurement. Okay, extremely low current measurement. Then how is it achieved? It is basically, if you remember that the instruments are quite bulky, it consists of magnetic field using permanent magnet, and then there is coil, and then there is pointer, and we to adjust the pointer we also have to have the counterweights, right? But in this case, it is avoided that the construction is similar to your PMMC, where you have this permanent magnet within which you have the frame, right? Frame over which you have the coil which is wound. This is the moving coil, right? And this is soft iron to increase the magnetic flux linkage between to the coil, right? So this is what we have seen. But what we have seen till now was that we had connected a pointer here, and along with that there was a coil. Now I'm showing it from top side. So this was a coil, this was the spring, and this is the pointer, right? This was used. But in the case of galvanometer, you don't use the mechanical pointer. So you don't use the mechanical pointer. What you use is that on the axis of rotation, okay, you attach a, so I'm trying to draw that. Imagine there is a mirror, okay, there is a small mirror which is attached on the axis of rotation, and you, what you need to do is that you put a laser beam, so not laser beam, you can put any light beam, and this beam will get deflected depending on the deflection of the mirror. And since mirror is connected to the rotating coil, that will deflect the light beam on a calibrated scale. Okay, this is a scale. Okay, now you can see that this light beam basically acting as a acts as a pointer, okay, or it behaves like a very lightweight pointer because the weight is almost zero now, isn't it? So it is capable of deflecting. So this reduction of the weight allows to deflect the arrangement even in the presence of very small amount of current. Okay, is microamperes. So this is where what we call these type of instruments are known as galvanometers, and they basically fall under PMMC instrument only. In fact, the similar principle, okay, the deflection of the light beam as the measurement of deflection, rather you can say, or displacement or rotation is utilized in, if I'm right, it is utilized similar principle in AFM for imaging atomic scale elements. Okay, for very small size, very high resolution imaging, this type of principle is also used. So the similar is used in galvanometer. And now the current sensitivity in this case is given as per microampere is the current sensitivity, because the what we are observing is the deflection in right? And what is the input we are trying to measure? Current, that is microampere. So per microampere is the current sensitivity. One important thing one must understand is that if you look at closely the mirror, if the mirror deflects by angle of theta, the total deflection on the of the light beam is of 2 theta. So 2 theta is deflection angle of light beam, and theta is deflection of mirror, and which is nothing but the deflection caused by the deflecting torque, isn't it? So you should be careful that when you are applying the formulation of PMMC, we use this theta, right? But what you actually measure is 2 theta. And how much is 2 theta in this case? So when you measure the deflection in let's say x, linear deflection. So theta of the pointer is theta by r, sorry, x by r. R is this length, the pointer length, laser beam length. But actual theta is theta p by 2, which is x by 2r. Please remember this part. Oh, this is important to remember. Fine. So this is a small thing I wanted to discuss associated with the galvanometer, which is nothing but a PMMC instrument. So from the next class, I will talk about a small thing related to thermocouple instrument, but I don't know whether I should do that because we have not yet covered what is thermocouple. So let us skip that part and probably go to electromechanical emitters, voltmeter and ohmmeter design from the next class. Thank you.
Sir, what about quiz date?
Hello? Yes?
Sir, you said you will announce the quiz date in the next class, in the last class.
Sorry, I could not understand what you mean.
Sir, you told you will announce the quiz date.
Quiz?
Yes, I mean.
Can we have quiz tomorrow during lecture hours? Okay, I think you have class now. I will discuss with your branch representative over Teams. Okay, thank you.